What we're looking at today is we're going to be talking about the quantum theory of the atom. Now, if you remember, we talked about Albert Einstein, and we said that he was the one who really put together this idea that it acted like an electromagnetic wave, but yet also had packets of energy. We're not going to call it the photon theory because in reality we had Planck, who was somewhat correct in stating that. So what we're going to do is we're going to talk about Niels Bohr. Niels Bohr went ahead and he studied the work of Planck and Einstein to come up with his model of the atom. Because again, Planck had the idea about energy, but Einstein was the one who put everything together. What he did was he developed his model of the atom by basing it on the hydrogen atom, because the key part about that was it only had one electron. And I want you to think back to physical science when we talked about electrons. If you have two negative charges, what happens? They repel one another. And that's the reason why he focused on hydrogen, because he knew he would have absolutely no repulsion. And what he really figured out was he came up with this conclusion that the larger the electron orbit, so the bigger in size that it is, the more energy that it had. The smaller the electron orbit, the less energy it had. It's kind of like the other video that you saw. When I was on the floor, I said, well, I'm at a low level. But when I stepped up on the chair, I said, well, I'm at a higher energy level. And when I stepped up onto the desk, I'm at the highest energy level. Okay, so I go from the floor to the chair to the table. And again, the higher you are, or the bigger the orbit you are, further from the nucleus, the more energy you're going to end up having. The lowest allowable energy state is going to be called ground state. Now, this is what I'm going to tell you. This is important for where we're going to be going. Electrons will always want to be at their lowest energy level. They don't like that extra energy. If an electron gains that energy and jumps to a higher energy level, that atom is said to be excited. The way I say it is, okay, you're walking around, hey, you're at ground state. But if all of a sudden you touch an electric fence, okay, that's going to shock you and you don't like it. So what do? You let go. You let go to lose that energy because you don't like that feeling. Same thing with the electrons. They want to be at ground state. They don't want to be at this excited state here. Electrons do not like being in that excited state, so what they have to do is they have to lose that energy. And the majority of the time that energy is going to be in the form of light. They have to lose energy, typically in the form of light, to get back down to ground state. That's why fireworks give off their colors. They're giving off that energy. They're giving off that light in their movement back down to ground state. Basically, it's explained by the following equation. The change in energy is going to be equal to that higher energy orbit minus the lowest energy orbit, or the energy at where it starts out at. That difference is going to be E photon. And that's what Einstein was talking about, or that's what Planck was talking about when he said, let's take H times V. Now again, I call it photon because that's really what Einstein was, put it all together when he said electromagnetic waves with quantums of energy. So again, you take that highest energy level and you're going to subtract off that lowest energy level. For example, if we say that that higher energy level is 5,000 and we say that this lower energy level is 3,000, well, 5,000 minus 3,000 is it has to lose 2,000 joules of energy. 2,000 joules of energy that is typically given off in the form of light. And again, that E photon, like I said, is going to be that light that's given off, or the amount of energy in light that's given off. Now, there were problems with Bohr's model. Okay, Werner Heisenberg studied the works of Bohr, and he studied the works of de Broglie, and he came up with a proposal. Basically what he said was, it's hard to put an actual value on the movement of an electron. So what he did was he came up with this uncertainty principle. Heisenberg's uncertainty principle stated that it's impossible to know both the position and the momentum of an electron at the same time. Here's what I'm saying. In order for me to know the position of something, I basically have to stop it. And if I stop it, that means it's not moving. Momentum is based on two properties, mass and velocity. And the minute I stop something, it has no momentum. And the minute it has no momentum, well, we know electrons are moving and do have a momentum. So the closer I know the position, the less I know about the momentum. Well, let's go on the flip side. Let's say that I study an electron's movement. I figure out its value. I take it times its mass and I get the momentum. But where was it during that time? It was in a multitude of positions. So the more I know about the momentum, the less I'm going to know about the position. Momentum, again, is the mass multiplied by velocity. Heisenberg stated that the closer you come to stopping an electron and knowing its position, you're completely uncertain about that object's velocity and you're not able to know momentum. But if you study the motion, you're going to be able to calculate velocity. If you calculate velocity, you can get the momentum, but you don't know where that electron was. Schrödinger furthered that wave-particle theory proposed by de Broglie, and Schrödinger derived an equation that treated the hydrogen atom's electron like a wave. That atomic model, in which the electrons are treated as waves, is called the wave mechanical model of the atom, more commonly today known as the quantum mechanical model of the atom. His model is based upon the region around the nucleus, or it's called the atomic orbital. And really what an atomic orbital is really a three-dimensional region around the nucleus of an atom. Schrödinger's equation is based upon four quantum numbers. And those four quantum numbers are N, L, M, and S. Now, I don't know about your education, but last I knew, N, L, M, and S, those were letters. But here's the thing. Those four letters, they're going to be represented by numbers. The first quantum number is N. N represents that principal quantum number. Remember those 7 rings that I talked about last chapter? This is what we're going to be looking at. It refers to the energy level that electron is in. Electrons can only occupy specific energy levels. You will never find an electron between two levels. Just like when I stood on the chair. I could never be between the floor and the chair. I either was on the floor or I was on the chair. Okay? I couldn't be in both. It's either in this level or that level, but it'll never be in between two levels. Now, theoretically, I want you to think about what the word theory means. Okay? Theory basically means what possibly could happen, what we're thinking, and things like that. Theoretically, we have energy levels of 1 to infinity, meaning we can have really as many as we want. Now, reality has shown that hydrogen only has 7 levels. Again, it goes back to those 7 rings that I was talking about. In order to get the maximum number of electrons in an energy level, what we're going to do is we're going to take 2 multiplied by n squared. And n is going to represent the energy level that we're in. Now, again, remember the math behind it. You have to square that level first and then multiply it by 2. So, if we're in the 5th energy level, 5 squared, 25. 25 times 2, that gives you your 50. Okay? So as I stated, we're going to square what energy level we are in. We're going to then multiply it by 2, and that answer will give you 50. I want you to tell me how many electrons, maximum electrons, could be in level 3, and how many could be in level 7. Now, I know I said 50 could be in that 5th energy level. What we're theoretically saying is it can hold 1, it can hold 10, it can hold 40, it can hold 50, but it cannot hold 51. So again, what numbers did you come up with for level 3 and level 7? The second quantum number, each energy level is going to be broken down into sublevels within that energy level. The second quantum number is L. L represents the sublevels. And what we're saying is these are also energy levels that are contained within a principal energy level. Now, theoretically, L equals N. So what we're saying is, if we're in the third energy level, if n equals 3 and n equals L, we can also say L equals 3. So the third energy level can have 3 sublevels. Again, theoretically, the seventh energy level will have 7 sublevels. Now, realistically, scientists have only found 4 known sublevels. Those 4 sublevels are S, P, D, and F. Now, you might be saying, well, those are letters, but again, each sublevel corresponds to a value. S will be 0. P will be 1. D will equal 2. And F will equal 3. Now, energy level 1, remember what I said. 1 equals 1. So, we're going to always start with the lowest sublevel. So, energy level 1 will have an S sublevel. Let's go up to energy level 2. Energy level 2, remember what we said, theoretically, N equals L. So, energy level 2, 2 sublevels, and again, remember that ground state. Electrons want to be at lowest energy. So, we'll have 2s and 2p. Third energy level has 3 sublevels. Again, we always start with the S. 3s, 3p, 3d. Energy level 4 has 4 sublevels. There they are. Again, going from lowest energy to highest energy. 4s, 4p, 4d, 4f. Now, like I said, there are only 4 known sublevels. In theory, there maybe should be 7, but we only know of 4 of them right now. So energy level 7 will have these same 4, 7s, 7p, 7d, 7f. Notice that you always begin with an S. Again, we always go from lowest energy to highest energy. Now, an S, basically what an S is kind of like what I was talking about last chapter. Basically think of this 1S as a 3-dimensional sphere, kind of like a ping pong ball. Okay, we go out here to the 2S. It also is a 3-dimensional sphere, maybe like a baseball or softball. And then all of a sudden we go out here to the 3S. Again, it's a 3-dimensional sphere. Maybe it's like a basketball. But again, the ping pong ball would be in the center of a softball. The softball would be in the center of a basketball. But all S sublevels are 3-dimensional spheres. Here's a P. Okay? Basically what we say is, and we'll talk about everything together, but when I go ahead and look at that one, we basically say it's like a dumbbell. Okay? So these are the 3 P's that do exist. Okay? Here's a D. Now that was the picture of all of them. There's 1, 2, 3, 4, and 5 shapes. Basically a D is going to have what we call a double dumbbell in shape. So we have a sphere, we have a dumbbell, and basically we have this one that we said was going to be a double dumbbell. And then I just go ahead and I put pictures of the F's up here. I'm not sure what you want to say, but notice that there are 7 different kinds of F sublevels. But again, we go from lowest energy to highest energy. Again, electrons want to fill those lowest energy levels because of ground state. Ground state is where all electrons want to be. They will always begin to fill lowest energy levels. Once that lowest energy level is filled, it will jump up to the next higher energy level. So, if we look at this, we would start to think that, well, 1s, and then we would go the two sublevels in the 2s and 2p. And then we'd go the 3 sublevels in the third energy level, 3s, 3p, 3d. Then we would go the 4 sublevels in the 4s, 4p, 4d, 4f, and so forth. Now, while scientists were researching, what they found out was actually 4s had a little less energy than the 3d. So really what they would have stated is this. They would have said, well, this 4 should actually come right here before the 3d. Okay, so again, they found out that there were problems when you list them in order of just energy level and sublevel. So while researching this, they found that a 4s had just a little less energy than a 3d. So it actually went 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then the 4p. Well, on the next slide, we have a mnemonic that's going to show you how really to use this. Okay, what you do is you list them out how really I told you. Now, again, I do want to go ahead and quickly fill in here. I know that we said that, again, there are only 4 sublevels. I really don't know why they left these out. Again, there should be a 7p here, and there should be a 7f also. And again, if you really want, you can think that, again, there is an 8s down here, there is an 8p down here. So again, you can go ahead and fill these numbers in. But basically what you do is you just list them. 1s with its 1 sublevel, second energy level with its 2 sublevels, third energy level with its 3 sublevels, fourth energy level, fifth, sixth, seventh, and eighth with all 4 sublevels. Then what you do is you basically come down like this. Okay, what did we cross? Well, we crossed 1s. Okay, we do that again. What did we cross? Well, we crossed the 2s. Okay, this one we're going to hit 2. First thing I crossed was 2p. Next thing I crossed was I crossed the 3s. Okay. Next one, I'm going to go ahead and cross. We get the 3p, and then I hit the 4s. And then notice that's how it went. It went 3p, 4s, and then here's 3d, 4p, 5s. So if you draw this mnemonic out and you draw your diagonals, it will tell you in order of increasing energy level which energy level and which sublevel comes first. So it says write the energy levels with the appropriate sublevel listed going from upper right to lower left, kind of like I showed you on the previous slide. So what you would end up here is with a 1s, 2s, 2p, 3s, 3p, and there's where that 4s comes before the 3d, 3d, 4p, 5s, 4d, 5p, 6f, and again, you can read. And this process is going to continue on and on. Now what I want to do is I want to do a little quick review over the first couple of quantum numbers here. What I'm going to do is I'm going to say that we have an electron that is sitting right in here. Okay, so we have an electron that's there. Now we've only talked about 2 quantum numbers right now, and those 2 quantum numbers were n and l. Now, we said that n represented the energy level. That's what this number is right here. Okay, the 4. The 4 tells you what energy level we are in. So, in this case, n would equal 4. Now, L represents the sublevel. Okay, L represents the sublevel. That letter right there will tell you what sublevel we are in. We're in the D sublevel. Now again, if you go back to look at those previous slides, we said S was equal to 0. Okay, so S equals 0. We said P is equal to 1. And we said D's are equal to 2. Now these are the first 2 quantum numbers. What energy level it is in, and then which of the 4 sublevels it is in, and a 2 is going to correspond to a D. Now we'll talk about the 2 final quantum numbers in the next video, and in talking about those we'll go ahead and throw everything together and seeing how all 4 quantum numbers work together.